The next section talks about the different geometries that a wave can have. If we think about the different types of source which could emit a wave, then we can think about the different geometries. So, for example, if we had a point source, excuse me, and that would then radiate out spherical waves, which would increase in radius, obviously, as they travel further and further away from the point source. And that means that the energy that's contained within one of these peaks, so these represent the peaks and the bits in between represent the troughs, then the energy is being spread out over a larger and larger surface area. So the amplitude of the wave will then go down. The amplitude gives you some relationship to the energy that the wave is carrying. So for a spherical wave, the wave will travel out as a sphere from a central point, and its amplitude will vary by 1 over r. So in other words, as r increases, then the amplitude of the wave will die away. Okay, so we'll get a 1 over r dependence on the amplitude. We can again write this as a sine wave or as a complex wave, and again we'll choose whichever one is the most appropriate for the particular piece of maths that we want to do. So A is essentially the amplitude of the wave. Sometimes you'll see in some books it's referred to as the source strength, and the modified amplitude then is A over r. So let's say as the wave travels out, then the amplitude of the wave will decrease inversely proportional to the radius. So that's a point source. We can think of also a line source. And so what we would have would be cylinders of light travelling out instead of spheres. Cylinders of light travelling out from a central axis. And again, as we get further and further away, then obviously the surface area will be larger, and that means then that the amplitude, the effective amplitude of the wave will decrease as well as a function of r, and in this case it goes with 1 over the square root of the radius. Okay. And once again we can write this as a sine wave or as a complex wave. So that's a 0-dimensional source, a 1-dimensional source, a line source, and now a 2-dimensional source. In other words, a plane source. A flat 2-dimensional plane, and it will give out flat 2-dimensional waves, and they will travel out in some direction, again some direction r. Now this time, if we assume that that plane is infinite in extent in terms of x and y, then obviously the area doesn't change as the wave moves forward. The area is constant. It's not increasing as it travels out, and so the amplitude of the wave is just given by A now. Doesn't depend on the distance r. That's the distance from the source. So plane waves are the most simple form of wave that we can describe, and so what we're going to do is we're going to assume that if it's a spherical wave, then the radius of curvature is so large that essentially over that sort of area we can think of the wave as being effectively flat. The curvature is so small that it behaves like a plane wave. And the same thing for cylindrical waves. So our plane wave description is the one that we're going to use for all the maths that we're going to do in later sections. If we think of the direction of the wave as being a vector, then we have to include that the product kr, where k is the propagation vector or the propagation constant, the product is now given by the dot product k dot r, rather than for a scalar we just had kr. And in Cartesian coordinates we can write that out. Gets a bit messy, but we have a wave propagation constant for x and the y and the z axis, and we have the overall magnitude given by the sum of the squares, all square rooted, adding the individual propagation vectors in quadrature. If we increase this to 3 dimensions rather than just thinking about one-dimensional travel, then travel along one of the axes, for example, then we have to also think about the wave equation, and the wave equation as it depends on space, and as we've seen before, as it depends on time. So instead of whereas before we just had the d by dx squared, now we have d by dx squared plus d by dy squared plus d by dz squared of phi is 1 over v squared times d2 by dt squared of phi. So second derivatives of x, y and z now. Now we can write that as something a bit more convenient, a bit more compact, and we write that as del, or the Laplacian operator. So del is d by dx plus d by dy plus d by dz, and del squared is just the second derivative. Okay. So that's for light which is travelling in a particular vector direction. The actual thing that's doing the oscillating, what does it represent? Does it represent a vector or a scalar quantity? Up until now we've just treated it as a scalar. If it represents a vector, then we have to think about the amplitude as a vector, and in which direction it's pointing with respect to the direction of travel as well. We'll see a diagram of that in a wee second. If the vector which represents the amplitude stays in one fixed plane, so as it travels out and it just stays in one plane, in other words, if we were looking in that direction as the wave comes towards us, all we would see is the wave vector pointing up and then down and then up and then down and so on. So if it stays in that one plane, then we describe the light as being plane polarized, or sometimes as linearly polarized. It has a fixed plane of polarization. So to fully specify the wave, not only do we need to know things like the speed of the wave, the wavelength, the period or frequency, we also have to think about the direction of the wave and the orientation of the amplitude as well, to get a full picture of how the wave is behaving. So what we've got here is we've got a little diagram of a wave, and it's travelling through space along the z-axis. and we can then break down that vector at some angle phi into an x component and a y component. Same you do with any vectors, you break it down into its x and y, and you can then describe the behaviour of this wave as the sum of x and y behaviours. So for a scalar harmonic in a particular direction where r is the vector which describes that direction, then we have a nice simple relationship that a times e to the I k dot r plus or minus omega t describes the wave. If it's a linear polarized harmonic wave, then a is also a vector, and that means that we have to think about how the wave, the peak of the wave, points with respect to its direction of travel. And again, you can put these into Cartesian coordinates, and in this case I, j and k are the unit vectors along the x, y and z axes, and again kx, ky, kz and so on.